All right, let's put on our detective hats today, because we are cracking open a case that took scientists centuries to solve: the mystery of the atom. We're going to follow the clues, piece by piece, and uncover the secret world hidden inside the very building blocks of our universe.
You know, for the longest time, the atom was seen as the absolute end of the line. The word itself, atomos, is actually Greek for indivisible. But what if that was all wrong? What if the atom wasn't some solid, unbreakable little ball, but actually a tiny container holding an even more amazing reality inside? Well, right around the turn of the 20th century, scientists started stumbling upon clues that suggested exactly that.
So where did this whole investigation even begin? How did we first start to see the cracks in that old, solid model of the atom?
Believe it or not, the very first hint came from something super simple: static electricity. You know how you run a comb through your hair and suddenly it can pick up little bits of paper? That little spark of magic is because the comb has an electric charge. And that led to a huge question: where is that charge coming from? The only place it could come from was the atoms themselves, and that meant atoms had to contain even smaller charged bits inside them.
And once that first crack appeared, the floodgates just opened. It kicked off this incredible flurry of discoveries. In 1886, E. Goldstein found these mysterious rays of positive charge. We later know them as protons. Then, J.J. Thomson comes along and pinpoints the electron, this tiny little particle with a negative charge. It took a few more decades, but the final suspect, the neutral neutron, was finally tracked down by James Chadwick in 1932.
So by the early 1900s, we had our first two subatomic particles in the lineup: the electron and the proton. And if you look here, you can see they have these perfectly equal but opposite charges. But here's the really wild part. Look at their mass. The proton is almost 2,000 times heavier than the electron. The electron's mass is basically, well, negligible. This was an absolute game changer. The atom was definitely not indivisible.
Okay, so now we have the pieces of the puzzle. The big question was, how in the world are they arranged inside the atom? J.J. Thomson was the first one to take a serious stab at drawing a picture of it.
Thomson came up with what we now famously call the plum pudding model. Just picture a ball of positively charged stuff, kind of like the cake part of a pudding. And then, scattered all through it, are the tiny, negatively charged electrons, just like raisins or plums. Some people also compared it to seeds in a watermelon. It was a pretty neat idea because it explained why atoms are neutral. All the positive and negative charges just cancel each other out.
It was a really clever model, and it fit all the evidence they had at the time. But in science, you have to test your ideas. And as fate would have it, one of Thomson's own students, a guy named Ernest Rutherford, was about to run an experiment that would just completely blow the plum pudding model out of the water.
And this brings us to a huge, pivotal moment in our detective story. We're talking about Rutherford's gold foil experiment. Honestly, it's one of the most important experiments in the history of physics.
The setup was surprisingly simple. Rutherford's team basically built this tiny little gun that fired a stream of positive particles, called alpha particles. And they aimed it at this incredibly thin sheet of gold foil. I mean, it was only about 1,000 atoms thick. According to the plum pudding model, those little alpha bullets should have just sailed right on through, no problem.
But that is not what happened. Yeah, most of the particles did go straight through, but some were deflected. And a few, about 1 in every 12,000, did something absolutely unthinkable. They bounced right back.
Rutherford himself was just completely floored. He famously said it was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. There was only one possible explanation. All that positive charge in the atom couldn't be spread out like pudding. It had to be concentrated in a tiny, dense core.
That shocking result meant the plum pudding model was dead wrong. It was time to go back to the drawing board and come up with a totally new model of the atom.
So, based on his mind-blowing experiment, Rutherford proposed a brand new model. First, he said the atom is mostly empty space, and right at the very center is this tiny, super dense, positively charged thing he called the nucleus. And the electrons? Well, he imagined them orbiting that nucleus, kind of like planets going around the sun.
But, you know, science is never that easy. This solar system model had a huge, glaring problem. The laws of physics at the time were very clear. An orbiting electron should be giving off energy constantly. That means it should spiral inward and boom, collapse right into the nucleus. But atoms are stable, so what was going on?
The solution to this puzzle came from another brilliant physicist, Niels Bohr. He came up with this really radical idea. He said, what if electrons aren't allowed to orbit just anywhere? What if they can only exist in specific, stable orbits, like cars locked into lanes on a highway? In these special energy shells, they just don't radiate energy. This was a massive leap, and it was our first real step into the incredibly weird and wonderful world of quantum mechanics.
Okay, so with a stable model of the atom finally on the books, scientists were right on the verge of cracking the code that defines every single element in the entire universe.
And the very last piece of our puzzle was found in 1932 by James Chadwick. He discovered the neutron. This is a particle that lives in the nucleus, right alongside the protons. It has about the same mass as a proton, but as its name suggests, it has no charge at all. And with that discovery, our lineup of the atom's basic parts was finally complete.
Now that we have a complete picture, we can finally define what makes each element unique, and it all boils down to one simple thing: the atomic number. That's just the number of protons in the nucleus. That's it. An atom with 1 proton is always hydrogen. An atom with 6 protons is always carbon. The atomic number is basically the element's unique ID card.
Next up, we have the mass number. This is just the total number of protons and neutrons added together. Since those guys are so much heavier than the electrons, the mass number gives you a really good idea of the atom's total weight. And this brings us to a really cool concept called isotopes. See, while the number of protons defines what an element is, the number of neutrons can actually change. For instance, every single carbon atom has 6 protons. That's non-negotiable. But some have 6 neutrons, some have 7, some even have 8. These different versions of carbon are all isotopes. Chemically, they're the same, but they just have different weights.
So, from a little bit of static electricity all the way to the discovery of the neutron, we have followed this amazing trail of clues that completely changed our understanding of matter itself. We now know the atom isn't some unbreakable little sphere, but this incredible, complex system. And that, of course, raises one last tantalizing question. Now that we know how to put an atom together, what happens when you decide to split it apart? The answer would change the world forever, but that's a story for another time.